We can start, please.
Okay. Yeah, hello once again. So today I'd like to tell you about Solidity functions, events, contract creation, and error handling in Solidity, how they work, and everything basically you need to know about functions, events, and etc. So we won't go into the deepest deeps of EVM, but we'll touch some not that simple topics. So if you have any questions, please just drop them in the chat, and I will answer them immediately. So first of all, what is a Solidity function? On previous lecture, we actually not in previous, but previous we discussed smart contracts in Ethereum, that they're like decentralized applications that they live on Ethereum, and EVM executes those contracts. And so those contracts have some kind of points of interaction, and those points of interaction are actually called functions in Solidity. So functions are like open endpoints of smart contracts, and anyone can call those functions, use them, interact with them, and etc., etc. It is fully a smart contract's responsibility to add proper access control checks and guarantees that the function execution is safe for the end user. So there are no firewalls, there are no DDoS protection of smart contracts. This all has to be handled by smart contracts themselves. If a certain function has to be called by an author of the contract, it has to be explicitly specified, because otherwise, because the code is open, everyone can read the code, everyone can interact with the code. For them, it is really easy to somehow alter the execution of the contract. So you have to explicitly specify what smart contract is allowed to do and what is not. Let's define a function in Solidity. So here I have two examples for you. The first one is an external function. The second one is an internal function. I'll talk about the function visibility on the next slide. But for now, we have to specify what the function signature is and what the function selector is. Function signature in Solidity, it is the name of the function plus the types of the parameters this function accepts. Function signature can be applied to both external and internal functions, but Solidity uses the function signature to build a selector only for external functions. So you won't be able to call internal functions from the outside, only external ones. And selector is a special value that Solidity uses to distinguish which function you are calling from the outside, so to enter the exact function you're calling, not to enter something else, and how Solidity calculates this selector. So it uses the function signature, passes the signature as a raw text, so it doesn't encode it anyhow, to Keshek 256 hash function, which outputs 32 bytes hash. And we take 4 first bytes of this hash. So this notation is taken from Python. This is slicing. So here I slice first 4 bytes of our hash. And this is the result I get. And this result is a 4-byte selector of the function, this one, function foo, which accepts uint 256 variable. And when you're calling smart contracts, Solidity has a list of those functions inside a smart contract. So basically, those selectors are placed directly into the bytecode. And when you're calling a function, Solidity will loop through every selector one by one. So those selectors are sorted. So it will loop one by one and check if the function you are calling is the one that has the selector of the function you are calling. And if it finds one, then it enters this function and does like argument decoding. So I'll talk about this a bit later. So yeah, you have to understand that the selector is some sort of unique identifier of the function that Solidity uses to distinguish functions from each other. What about functions and variables visibility? So functions can be external, public, internal, and private. And variables can be public, internal, private, and default. So here, on our example, we have a variable counter, which is declared as public. So this means that this variable is readable from the outside, but this doesn't mean that someone can write into this variable. So only the contract itself is allowed to modify its storage. So no other contract is allowed to modify storage of another contract, only itself. And here is the function increment of the name increment. It is declared as external. Yeah, it returns something. So here it just increments the counter and returns the next counter value out of the function. So external functions are the ones that can be called only from the outside. So you wouldn't be able to call external function from inside of the contract, except one case that I will also cover in like next slides. Public functions are the ones that can be both called from the outside and from the inside of the contract. Internal functions are the ones that can be called only from the inside of the contract and as well from the descending contracts. So from the contracts that inherit your contract. And private variables and functions are the ones that can be called only from the scope of your contract. So even descendants like are not allowed to call private functions of their parents. Variables can be public, so this means that Solidity will generate the getter for this variable for you. So you like wouldn't need to write your own getter for this variable because it is automatically generated. Internal ones, as well as the functions, are only accessible from within the contract and from its descendants. Private, only from within the contract, and contract's children are also unable to accept those variables. And default visibility, it is when you are not writing the visibility modifier at all, and default visibility in Solidity is internal. Okay, speaking of function modifiers, there are several built-in function modifiers into Solidity, and also you're allowed to declare and use your own modifiers. So how do they work? So first of all, we have view and pure function modifiers. These are the ones that limit like the ability of the function to change the state of the contract. So if your function is declared as view, it means that this function is not allowed to change the state. It is only allowed to read the state. Also, it's like not allowed to create contracts or other contracts if they modify state. So it is only allowed to read state and call other view functions of other contracts. Pure functions are the ones that can't even read the state. And also, these functions are not allowed to read the global state. For example, you won't be able to know the message value of the call. So those functions are usually used for like some kind of utility calculation in libraries. So when you are like calculating some formulas and something like that. Payable functions are the ones that are allowed to accept ether when called, and by default, every function in Solidity is non-payable. So you won't be able to call this function and provide ether to it. So if you want one, then you will have to like explicitly specify that it is payable. Then there are override and virtual modifiers. So these are the ones connected with inheritance, and we will cover those modifiers in a later lecture when I will be talking about inheritance in Solidity. And also, you can declare your own modifier. So here I declare modifier only owner, and I check inside the modifier that owner, which is set in the constructor is executed when the contract is deployed. So the sender of this deployed transaction is message sender, and the owner is set to this message sender. And in the modifier, I check that the owner is message sender of whatever call it is. And then there is this special construction, which is underscore semicolon, which basically means that the function this modifier will be applied to is going to be placed instead of this strange syntaxes. So we have a change owner function, and here is the only owner modifier that is set to this function. And inside this function, I change the owner. So what happens here is because inside the modifier, we have this underscore semicolon after the require statement. That means that our like equivalence, our change of owner will be executed after the require statement. Yeah, so basically the body of the function is placed instead of the syntaxes. You can also add like as many underscores with semicolon as you want. So there in this modifier could be like 5 underscores or 7 underscores, and that would mean that 6 or 7 bodies of this function would be executed. So that's it. So this is just like syntax sugar, and what it means is that this function, change owner function, is only callable for the owner. And only owner is allowed to change the owner. So something like that. Also, I will talk about optimization in Solidity probably on the next lecture. and I will cover that the usage of modifiers may increase the byte size of the contract and how to properly deal with that. Okay, so let's quickly talk about the creation of contracts inside the contracts. So there are two ways to create contracts. Right now, for those ways, there are opcodes. The first one is create opcode. And basically, the difference between those two methods is how the contract, how the output contract address is calculated. So if you're using create opcode, then the resulting address after the creation will be the catch-hack 256 of the RLP encoded sender. So here the sender is our contract, our example contract, and the nonce of this contract. And we are taking the last 20 bytes of the hash. So here we are slicing the first 12, so taking the last 20. Nonce, in terms of smart contract, is the number of contracts it has already deployed. And the counter, the nonce counter, starts from 1. So this is different from externally on account nonce, where this nonce starts from 0, but contracts nonce starts from 1. But still, if you are deploying contracts from the outside, if you're a user who is deploying a contract, the address is still calculated according to this formula. What is bad, in quotes, with this approach is that the address of the contract depends on the state of the blockchain itself, because this nonce is the counter of how many contracts or transactions in terms of external on account you have sent or deployed. And this is the state of the blockchain. So, for example, you want to know for the future which address this, some random contract will be at. But you can't be 100% sure, because you might send a transaction somewhere, your nonce will be incremented, so the address will change. So this is not really good for from blockchain standpoint, because it is not deterministic. So to overcome this issue, the opcode create2 was introduced, and it uses a different approach to calculate an address of the contract. And this opcode is only available within the contract. So you won't be able to use this opcode if you're just a regular user who is deploying a contract. So it is only available for the contracts. And the address is calculated as catch-hack 256 hash of concatenation of, this is just bytes. So these bytes with the sender address, so on example, this is our example contract, then special salt, and the hash of the creation bytecode of the contract that you are deploying. And also you are taking the last 20 bytes of the hash to get an address. So this is completely deterministic, because the creation here relies only on the bytecode of the contract you're deploying, the salt, and the sender address. So that's it. And using those parameters, you are able to pre-calculate where the contracts will be deployed off-chain and somehow like react or use or like write your own like business logic to somehow use it. So here in our example, we have 2 lines of code that deploy contracts. The first one is the deployment with the creative code. This is how Solidity handles it. And here is the deployment of the contracts with the creative code. So the difference here is that we are passing salt to the, like, using salt as a syntax. Yeah. So we have created contracts, then we have to or need to call these contracts. So how to call contracts in Solidity? There are actually a lot of ways how to call those contracts. So here we have an example of the interface of Kali interface, and here I declared function foo. So this function has no body, it is just a declaration. And here we have a function test call, which accepts the address of the contract we would like to call. So here it is this one. And here is like the regular high-level call that everyone uses to interact with other contracts in Solidity. So we are casting the address to the interface Kali and calling function foo with an argument 1. Yeah, so what is great about this high-level call is that if something went wrong inside this foo function, this call will also revert. So using this high-level syntax to interact with smart contracts is safe, because if the Kali contract reverts, the caller contracts will also revert. And here we have 4 lines of low-level interaction with smart contracts. So the first one, it is the low-level call, but so it is the same call as this high-level one, but the low level. So we are using the variable Kali, and address as a built-in Solidity type has several functions to like interact with it. One of them is call, and call accepts like raw bytes which to pass to the Kali contract. So from the previous lectures, I hope you remember that when you're calling a contract, at least in Solidity, those arguments, this call has to be ABI encoded. There are built-in ABI functions in Solidity. They are globally available. So here I use ABI encoder to encode the function call. It uses, so this function called with signature uses the function signature as the first parameter, and then the arguments of the function after the first parameter. But here we have only one argument, so only one additional argument is needed. So this thing encodes the function call via ABI encoder, and then this call passes those bytes to the Kali contract. What is important is that low-level calls never revert. They return Boolean argument, whether the call is successful or not. So here in this example, for the sake of simplicity, I don't check the success of the call, but in production code, this is a must. So you have to check the so whether the call is successful or not. yeah, so this line of code does everything like, so it works the same way as the one above. Then there are 3 different calls in Solidity or in EVM. The first one is a delegate call. It is the call that proxy contracts use. We'll also talk about proxy contracts in future lectures. But yeah, here I like to show that you can also encode with different functions. So not only with the encode the signature, but also with encode the selector. And here is how you can obtain the selector of the function. So it is cali.foo.selector. So just like that. And I will talk about the differences of those calls on the upcoming slides. So yeah. Then there is a static call. So static call, it is like the same as call, but it is used to call view functions. So Solidity automatically understands which opcode to use, call or static call, to either call view functions or non-view functions. And also there was a call code, opcode. Actually, it still is, but it is like deprecated and shouldn't be used. And also you can like use it to call functions. So just like that. And here is the differences between all of them. I will quickly go through them, not going into like the depths of the calls, because yeah, we'll talk about, for example, delegate call when we will cover proxies. So here is the like a diagram, the like a tiny one on the bottom, with a table that is built from the context of the B contracts. So the user initiates a transaction which calls contract A, and contract A uses those opcodes, different ones, to call contract B. Here the arrow is in purple and opcode is also in purple. So if contract A uses call opcode, then the storage of the contract you're calling will be used. The sender and the value, the message sender and the message value, will become the A contract. So this is basically the regular call. Yeah, contract A calls contract B. B, the storage will be used. A becomes sender. B bytecode gets executed. So regular call, nothing new, nothing special. Then there is a delegate call. So when contract A calls contract B, the storage of contract A will be used. So not of the contract B, but of the contract A. The sender and the value of the call will be used of the previous call. Yeah, so basically the like message sender inside the B execution context will be the user, but not the contract A. And the bytecode of B contract gets executed. So basically, delegate call does what? It uses bytecode of the contract B to change the storage of the contract A. And the bytecode of contract B, if it, for example, reads the message sender somewhere, the message sender will be the user, so the previous one. And this is like the way proxies work, but yeah, we'll cover them in the future. So the static call is the same as call. So you can see that the storage of the contract B is used as in the call. The sender becomes the actual contract that initiated this call, and the bytecode B is used. So regular call, which doesn't allow storage modifications, only storage reads. And the deprecated call code, which works kind of like as delegate call is, but the sender and the value is like gets changed. Yeah. So in delegate call, we are calling the contract. The storage remains the same. The sender and the value remains the same. But with call code, the storage remains the same, but the sender's value changes. And this was like not as useful, so it got deprecated like long ago. So it's just for the sake of history, but yeah, you should never use call code anymore. It was deprecated in favor of delegate call. Okay. So there is one tiny difference in Solidity about function calls. And this question is, for example, usually asked during interviews. So what is the difference between those two lines? When you're using this dot bar, it's call function bar, or you're like calling directly with a bar. So here the function is declared as public, which means that it can be executed from the outside and from the inside. It can be called from the outside and from the inside of the contract. But what is the difference? The difference is if you're using the first index, this dot bar, this creates a full subcontext. So this basically means that you're using opcode call to call this function. So the message sender inside the bar function will be the address of the example contract because it has called itself. But when you are calling the function like that, the message sender doesn't change. So here, the message sender will be the guy who called the full function from the outside. And this internal call is not a call, but basically like jump to where in the bytecode this function is declared to be executed first. So something like that. Using bar is much cheaper, but sometimes you have to use this syntax as this dot bar to like do some advanced stuff, like calling the contract or calling like yourself, yeah, from the external libraries to do some optimization. So yeah, it is like an advanced topic. So like 99% of time, this dot bar shouldn't be used. Okay. Quickly about ABI encoding, because yeah, you have to understand how exactly the functions are called and how Solidity understands what to do. So ABI encoding is actually a complex encoding because there are differences between types. So in Solidity, there are two categories of types, the static ones and dynamic ones. So static types are like regular address, uint 156, uint 8, byte 32, like etc., etc. And these types are encoded in place. So this means that if you're encoding this type, it will be directly translated into some bytes. So I will explain how those bytes work. But if ABI encoder sees dynamic type, so dynamic type is, for example, dynamic array, struct with dynamic arrays. What else? Yeah, maybe bytes and strings. So bytes, strings, dynamic arrays, and tuples with dynamic types inside. So these are all dynamic types. And those dynamic types are encoded like the two-step encoding is used for dynamic types, the encoding of head and encoding of tail. For static types, head is the actual encoded value of the static type, but for dynamic type, head is the offset of the encoding, and tail is the actual value of the dynamic type that is encoded. So here we have a simple example of encoding. There are no dynamic types here, only static ones. The function that we are encoding is deposit, which accepts address and uint 256. And we have two parameters here, the message sender and one with 18 zeros. Yeah, this is just syntax trigger in Solidity. And I'm using code with signature built-in Solidity function. So what we have on the outside is the 4 bytes of function selector. So if you're encoding a function, the first 4 bytes are always the function selector. And after that, the function arguments are encoded. So these are static types, so they are encoded in place. And ABI encoder always pads the non-32-byte long parameters to 32 bytes. So address here is 20 bytes long, and the address is encoded like from left to right. Yeah, so the lowest bits are on the right and the highest bits are on the left. So this means that if we pad this address to the left, the value is unchanged. Okay. So what Solidity does is that it adds zeros to our address. This is actually the message sender I used. It is the first count in premix, if you're wondering. So these are bytes of our address, and Solidity added the address to 32 bytes. This is the first parameter, and the second parameter is the hexadecimal encoding or representation of this value. And here it is. It is also padded to the left. So, for example, if we used not uint 256 here, but for example, uint 128, Solidity would still pad it to 32 bytes. So even though 126 bits is not 32 bytes, it's like 16 bytes, yeah? But ABI encoder would still pad it to 32 bytes and add those zeros to the left of the number. Yeah, so there are many examples of ABI encoding in documentation. You can, for example, check the documentation or just open the random transaction on Etherscan and inspect the ABI encoding yourself. So when the contract gets called from the outside, it will the data that is used for the call will be encoded just like that. But depending on the function complexity, it may be really hard to understand what's going on, because here we have only static types, but with dynamic types, I will have like offsets from the beginning of the data, where to find the tail. Then if there is another dynamic type inside the dynamic type, then there will be two offsets. So yeah, it is really hard to understand where the parameter actually starts, where the head of this dynamic parameter ends, but still you can check and try yourself. What is important is, for example, Boolean parameters are not used in ABI encoding, and instead uint8 is used. So if your function accepts Boolean parameter, ABI encoder would encode it as uint8. Also, there is a built-in utility into Solidity, which is called enum. Enums are also encoded as uint8. User-defined structs are encoded as tuples. So the actual name of the struct or struct is not used, and instead the tuple or tuple is used, and the parameters of this tuple are also included inside this tuple. Yeah. Also, there's mentioning that static arrays, where the length is known, are encoded as well in place. So static arrays are static. So having a static array of 10 addresses is the same as encoding 10 addresses by one by one. Okay, so we have talked about creation of contracts, about functions. Let's talk about events. So what are events? Events are an abstraction on top of EVM login functionality, which is used in the applications off-chain to listen to those events and somehow react. These events and listeners are available via standard RPC interface, often a Ethereum client. So basically, these are special functions that you can call with the keyword emit to notify the EVM that it has to save something into a special data structure that is accessible through the RPC interface for filtering, subscribing, and finding, quickly finding the value of this event. So basically, it is the logging of what has happened with the smart contract during its life. Many off-chain applications use this functionality. For example, the graph is like a decentralized database that you can program to listen to events on certain contracts and react to those events. So here we have a receive function, which accepts Ether because it is payable. And once Ether is sent to the contracts, we emit an event that we received Ether and pass message value to the one and only parameter of the event. So just like that. Yeah, so Solidity has certain modifications of the events. The first modification is indexed parameters, and the second modification is anonymous events. So what does indexed mean? Events have special topics that applications can filter events by. So these are like special event parameters that are placed into the highly optimized data structure that can be used to quickly find information from or distinguish events from each other really quickly. So in our previous example, we didn't have an indexed event. So this parameter will get ABI encoded and just placed into like a special data location where every parameter like is encoded and placed there when the event gets emitted. So applications subscribing to those events will have to decode those parameters using some software or decoders. But here, on our example, I added the indexed parameter. So this means that our amount won't be placed into the special location, and it won't be ABI encoded. It will be just the amount that we passed. And indexed parameters or topics can only hold the values up to 32 bytes. So if we had like a huge array, like say array of 10 elements that we declare as indexed, Solidity would hash this array with cached 156 hash function and place the hash of this array into the topic, not the whole array. So using normal events, we have 3 topics at our disposal, and using anonymous events, we have 4 topics. So what is an anonymous event? Here is the declaration of an anonymous event. And what it basically means is that the 0 topic, so topics, enumeration of topics starts from 0. So the 0th topic or non-anonymous event is an event signature. So it is the hash of the signature of the event, and then first 4 bytes are taken and then placed, or actually might be not first 4 bytes, but actually the hash of the event is placed into the topic. But for anonymous events, this topic is not used, and users might populate this topic with whatever they want. But this means that the outside application won't understand which event got emitted. So that is why it is anonymous. Emitting those events, emittance of these events are the same. Yep. So we have something in the chat. Will this event be still emitted if message value is 0 or even empty? Yes. So we'll have a lecture about fallback and receive functions. This is the same lecture that I will use to talk about proxies. So if quickly receive function gets called when the data of the function, or so when you're calling this contract, you're specifying some data to use. So if this data is empty, then the receive function is called. So you can call it with empty data and zero value and still call this function. But if the data is specified, so anyhow, like anything, if you just use anything in the data, receive function won't be called, and fallback functions will be called instead. Because there is no fallback function in this contract, you will get a revert. Okay. So let's talk quickly about error handling in Solidity. There are three types of error handling functions in Solidity: require, reverse, and assert. There was a throw function in like Solidity 4, but it got deprecated in Solidity 5, and you can't use it anymore. And you actually shouldn't use it because it was deprecated in favor of require, revert, and assert. Also, assert used to consume all the provided gas of the transaction when used. But in Solidity 0.8.0, this was changed. So right now, assert doesn't consume the whole supplied gas to it. It is just, so it works like a revert. But a bit differently, I will also talk about it on the next slide. So here we have a function deposit. It accepts token to deposit and some amount to deposit. And here I check that amount is greater than 0. Here I use assert. This is just for the sake of example. Assertions mustn't be used to check like some like the correctness of the function calls or the correctness of parameters. So assertion should only be used in the cases where, for example, division by 0 shouldn't happen, or where the built-in something like really low level shouldn't happen, or the user access control require has to be used. But yeah, still. Then there's an example of the revert usage. Here I check that if the token that user provided to the function is not in the whitelist, some imaginary whitelist, then we revert with the custom error. In Solidity, you're also allowed to declare custom errors. So here is how you declare one: the keyword error, the name, and the parameters. So just like events, but errors. And you can use those errors to revert. So basically, what will happen here is this error will be ABI encoded and placed into return data. So applications that check the reverse statement would have to decode the return data and understand which function or which error was thrown. And then I use a transfer from function, which is the function from the ERC20 standard. And I am transferring tokens from message sender to address this, and I'm transferring amount of tokens. So by specification, ERC20 transfer functions return true if they are successful and return false if they are not. But this is like usually omitted because like 99.9% of tokens revert if something went wrong. But if we are following specification, we have to double check that. So here I placed a require on top of the transfer call and check that return is successful. So that it returned true. So if this transfer is true, then requirement passes, everything works. But if the returned value is false, then the transaction reverts and places this string into the return data. Yep. Okay. And it is first mentioning the try catch functionality in Solidity, which you can use to like somehow catch errors and react to the errors that other contracts made. Yeah. So try catch functionality only works in two cases. So you can use it only in two cases. First one is an external call, and the second one is the smart contract creation. So here we have a function foo that tries to call the do revert function. Do revert function reverse. If the call is successful, then the execution continues in the try block. But yeah, it won't continue here. So one of those catches will be used. Which one exactly? The first one, the catch error, is used only when the high-level revert happens. So what I mean by high-level revert is our revert with the message in quotes, or the require statement with the message in quotes. So here we can catch this message right here. The panic revert is used when assertion fails. So it is either when you are trying to divide something by 0, if you're trying to access an array out of bounds, or if you're using the assert from the previous slide, this assert. In either of those cases, the execution continues from here, and the dedicated code is used to understand what happened. So if none of those cases pass, either of those two blocks is executed. So here I place them one by one, but this won't work. Solidity won't compile here, but it is just for the sake of example. So those two catches are equivalent. In the first one, this is the one that is used for the custom errors catch. So here I have a declaration of a custom error, and if you throw this custom error here, it will be caught here with the ABI encoded error. So you'll have to manually decode it. And this catch statement with the which accepts nothing is the statement that is used to catch everything, just like one above, but without the reason. So sometimes it is useful not to know the reason. So here you can use it just like that. Yes, one important note here is that if the revert happens inside the try block, so inside this exact call to the external function, then the try catch doesn't work. So it only works when revert happens inside the context that you are calling. If revert happens in the current context, then like it just reverts. So it won't go into the try catch block whatsoever. Yeah, and really important pattern in Solidity. Its name is checks effects interactions, or CEI, and it is really important to follow Solidity best practices. So CEI pattern is the one of them. So can you spot and exploit here in this contract? So if you're watching this video, you can also pause it to check yourself, but yeah, here I will just explain what's happening here. So we have a deposit function that is payable, and users are allowed to call it with supplying Ether to the function. So we'll be just adding this Ether to the balance of the user. But here in the withdraw function, so everyone is allowed to call it, and what can happen here? User deposited some Ether. Let's say they deposited 1 Ether. So there is 1 Ether on their balance. This exact user calls withdraw function. And we are using the low-level call to call this user and return him or her the deposit they provided. But what happens here is that we give the execution control to the caller. And what they can do is they can use this execution context to call the withdraw function once again. And this attack is called a reentrancy attack. So what will happen is that we'll send them 1 Ether, which they own. They will re-enter into our contract. And then we will also send them 1 more Ether. They will re-enter once again, and we will send them 1 more Ether again. So they are basically successfully draining our contract. So why does it happen? Because we are not following the checks effects interactions pattern here. We are doing interactions before effects. So instead, we should delay the deposit of the user before calling this user to mitigate this attack. But here, we failed to do so. So there is an exploit, which is basically a critical vulnerability. And what is cool is that you will have to implement this critical vulnerability and implement an attack to the contract in your practical task. So it should be a lot of fun. Yeah, so if you have any questions, please ask. If not, then thank you for the lecture.
Okay, thank you a lot, Artem. And I think our students are waiting for our new task. Today or tomorrow, it will be done. Okay, so now after this time, I will add this presentation and waiting for our task. Thank you so much. Thank you, Yuna. So, bye-bye.
Yeah, bye.